right? First order non-homogeneous differential equation. And we're going to use Laplace to show you how to solve this. So watch the steps. It's very simple. You start by taking the Laplace on both sides of the equation. So you take the Laplace. Let's use this L. Okay. Of dy over dt minus 2y. Okay. And then you take the Laplace of e to the 5t. Okay, so you take the Laplace on both sides, and here I can take the Laplace of the first plus the Laplace of the second, because you know this is a linear combination. Now let's talk about, so this becomes the Laplace of dy over dt, no, minus 2 is a constant, it comes out, the Laplace of y equals the Laplace of e to the 5t. Okay, what is the Laplace of dy over dt? We've seen that in the very first section, right? The Laplace of dy over dt, if you remember, was s times the Laplace, can you see? Times the Laplace of y of t let's put this in brackets, minus the initial condition y of 0, if you remember. That's the Laplace. Okay. So now let's, and then of course the Laplace of, what's the Laplace of y of t? It's just y of s, which is what we're after. Okay, so this here becomes s. Okay, let me actually rewrite it down here, it's better. So that means the Laplace of dy over dt is s times the Laplace of y of t is just y of s minus y0. What's y0? The initial condition. At 0 it's 3, so minus 3. Okay, so now we're gonna plug back everything back here into equation star. So substitute into star. No, let's change the color. So we're gonna get a star says L dy over dt, so that's s ys, right, minus 3, and then minus 2 times the Laplace of y, which means minus 2ys, equals, okay, what is the Laplace of e to the 5t? Because the right hand side is the Laplace of e to the 5t. Here we go back to the table. So the tables, you look here and you look for e to the at. So that's 1 over s minus, what's a in our case? Was it 5t or 3t? Yeah, 5. So s minus 5. Okay? Now the objective is to get this guy right here. Because once we have this guy, we take the inverse Laplace like we were doing on the previous section, we get y of t, which is the solution of the differential equation. So we'll keep those on this side since they both have ys, and this 3 can go on the right hand side. So then we will get y of s, and I'm going to factor out y of s from these two terms here. So we get s minus 2 equals 1 over s minus 5 plus 3, because I added the 3 to both sides.
Yeah.
Okay? And now what I'm going to do is I'm going to divide. First, I'm going to take a common denominator here between these two. So this is s minus 5. This 3 multiplies the s minus 5, right? Because this is 3 over 1. So simple algebra here. So this becomes 3s minus 15 plus 1 will be minus 14. You agree? And this is y of s times s minus 2. And now I'm going to divide both sides by s minus 2. So I get y of s to equal 3s minus 14 over s minus 2 times s minus 5. This is my y of s. And how do I get my y of t from this? Taking the inverse Laplace. If you take the inverse Laplace of y of s, you get, conveniently enough, y of t, which is the solution for your differential equation. Now, of course, the question now becomes, how do you take the inverse Laplace? And this is going to require some algebra, because the table doesn't have anything in this form. So to take the inverse Laplace, let's use the green on this, okay? So to take the inverse Laplace of 3s minus 14 over s minus 2 times s minus 5, we're going to have to do partial fraction decomposition on this guy. Partial fraction decomposition. Remember, calculus 2, and you may have taken it in calculus 1. And then when we have it partially decomposed, hopefully, yeah, some people, yeah, some of them teach it in pre-calc. Then we can take the inverse Laplace of each piece using the tables, and we'll get there. Right. So now then, we're going to do partial fraction decomposition. So 3s minus 14 over s minus 2 times s minus 5 is equal to a over s minus 2. There exists two numerators, a and b, such that a over s minus 2 plus b over s minus 5 has to equal the original. Okay? And now I can take a common denominator between these two. And a gets multiplied by what it doesn't have, s minus 5, and b gets multiplied by what it doesn't have, s minus 2, over the same denominator. So this is really algebra here. I'm gonna, because this class is way beyond algebra, so I'm gonna try to do the algebra in somewhat of a quick way. So these two go away, and then we have 3s minus 14 equals as, you're going to FOIL now, minus 5a plus bs minus 2b, and I'm going to collect the s's together, so these two together. So this is the same thing as a plus b s minus 5a minus 2b, and this has to equal 3s minus 14. Now, the only way these two polynomials could be the same is if you know what's coming here, yeah? If these two are equal, the coefficient of the s, and the constant equals the constant. So this gets me two equations and two unknowns. Because I'm after the a and the b, basically. So I can split the, do a partial fraction decomposition to take the inverse Laplace of each one. So with that said then, that means a plus b has to equal 3, and minus 5a minus 2b equals minus 14. Okay, high school algebra, two equations, two unknowns. You can either use substitution or elimination, whatever you like. I'm going to multiply this equation by 2, okay, and put it here. So then I will get 2a. I'm going to use elimination, so plus 2b equals 6. Right? Everything solid so far. Okay, and then I'm going to add here. So the b's go away, and I get minus 3a equals minus 14 plus 6 is minus 8. So that just means a is 8/3. No? And plug that back into the first equation. We get b equals 3 minus 8/3. So that's 1/3. Okay, so now our original fraction becomes a over s minus 2. So that's 8/3 times s minus 2. No? And the second one is b over s minus 5. So b 1 over s minus 5. And of course, the job is to take the inverse Laplace of each one. Since 8/3 is a constant, I can pull it out, right? So we're going to take the inverse Laplace of this plus 1/3. Let me leave this here out. The inverse Laplace of this, because that's what this became. And now those can be easily gotten from the table because they're fairly straightforward. So you can see that this is 8 over 3, 1 over s minus 2. A is 2, so this becomes e to the 2t plus 1/3. In this case, a is 5, so you get e to the 5t. And this is what? This is your inverse Laplace of ys, which is what? Which is y of t. So therefore, to conclude, y of t is equal 8/3 e to the 2t plus 1/3 e to the 5t. What's actually interesting about Laplace transform is that it gives you the solution with the coefficients already solved for. You don't have to go back and substitute initial conditions to find the coefficients C1 and or C1 and C2. It already takes care of that in the process. So you don't have to do any algebra at the end. So you can see here, I got my coefficients. Well, in this case, I would have 1. No, I would have, no, because this is non-homogeneous. I would have 1 for the complementary, and I would have 1 for the particular. And in this case, Laplace spits out both of those in the process of doing it. Okay, so this is an example on how to use Laplace transform to figure out the solution for a non-homogeneous first-order linear differential equation.